In this video, I want to talk about what happens when we combine mixtures of gases. And that brings us to another law. This one's called Dalton's law of partial pressures. So it states that the total pressure exerted on the containers of a or the walls of a container the sum of all of the partial pressures that each gas would exert if they were totally alone in that container. Um, which is to say that the pressures of gases are additive. And this really gets back to Avogadro's law that when we added more moles of a gas, the volume expanded, right? And if we constricted that volume and we made it a rigid container and it was constant, when we looked at the demonstrations, we saw that the gas pressure would increase instead if the volume couldn't increase. And in our demo, we then saw a little carbon dioxide canister like, right, explode open. So we're going to assume there's not any explosions happening here. But we can write this out in this way right here, where like the total pressure of a system is going to be equal to what we call the partial pressures of the individual gases that make up the mixture. Now, partial pressure is going to be the pressure of just one of the gases in the volume that the mixture occupies. So here, if I have a mixture of three different gases, that's what this picture is trying to show you. If I have like the same, they're all in the same container. If I just imagine that all the other gases go away and I just have one of them, the pressure that that gas would exert would be its partial pressure in that system. And then each of these, if they have different amounts of gas in the same volume, will have different pressures, right? And to figure out when I combine all of them in the same container, then what I've done is I've just added more and more particles. So as I'm adding more and more particles, I expect the pressure to increase, right? And so the pressure that's our final pressure for the mixture is going to just be the sum of those pressures of the gases on their own. So in this case, and it might be too small to see in the video, we've got about 300 kilopascals of one gas, then 600 of a second, and 450 of a third. So if I combine all these three in the same container, then my combined pressure is going to be 1350 kilopascals. Another way to write this and think about this that I really like is with the ideal gas law, that there is this relationship between the moles of a gas and the pressure of a gas. And so we could say that the total pressure is equal to the total number of moles of gas times R and T divided by V. This would also then mean that the pressure of just one of the components, so the partial pressure, would be equal to the moles of just that component times RT divided by V as well. So here's an example to look at. Let's look at air, dry air. Um, so again, we have our Dalton's law of partial pressures right here. So in terms of just like the air around us, its composition is mostly nitrogen. It's about 78% nitrogen, 21% oxygen. There's some argon in there, about a little bit less than 1%, and a little bit of carbon dioxide. There's also there's a percentage of water vapor in there, and the amount of it really depends on the humidity, right? So when we say dry air, we mean air without water. So if this is our percent by volume for that dry, waterless air and its composition, we can make an assumption if we want to know the partial pressures. If we know that the total pressure of all of our gas is 1 atmosphere, right here, so the pressure of our air is 1 atmosphere, that means we're probably at sea level. Then we can say that the pressure, the partial pressures of all those components that make up air has to equal 1. And so that means that we're going to have a partial pressure of nitrogen, that's 0.78 atmospheres, a partial pressure of oxygen, that's 0.21, a partial pressure of argon, that's 0.009 atmospheres, and a partial pressure of carbon dioxide, that's 0.0004 atmospheres. And so that total mixture, the percentage of each of the components that make up that mixture will be the atmospheres that they are. So if we're curious about what is the partial pressure of nitrogen in air, well, the partial pressure of nitrogen in air is going to be 0.78 atmospheres. Another way we can represent this, sorry, for Windows, is with mole fractions. And we'll use this in a few places. So a mole fraction we've talked about in terms of concentration already. And we raised this when we talked about concentration of solutions. And we use mole fraction as a way of tracking concentration in gases and gas solutions. So it's going to be the ratio of the number of moles of any component gas to the total number of moles in the mixture. So this is going to be the same then as that partial pressure ratio as well. So when we looked at our equation for the ideal gas law and framed it in terms of either total pressure or partial pressure, right? We have, this is that equation we were looking at right there. So our mole fraction would be equal to just the moles of one of our components over the total number of moles for the entire mixture. And that's really right here in our equation. And that component is proportional to, it's equal to that same ratio of just the partial pressure divided by the total pressure. These RTVs, these cancel out, right? And so the ratio of our partial pressure to the total will be the same as the ratio of the number of moles of a component gas to the total number of moles. And so both of these are going to represent a concentration represented as mole ratio, or sorry, mole fraction. Same as like pressure fraction, but we call it mole fraction. Let's continue our example of looking at air, dry air. And we already saw the composition of this based on partial pressures, taking it from our total pressure and the percent composition of gas and the air around us. We can calculate the mole fraction of nitrogen. We determined that the partial pressure was 0.78 atmospheres at 1 atmosphere of air around us. So to calculate that mole fraction, what we're going to do is just take that partial pressure of 0.78 atmospheres and divide it by the total. In this case, it's simple because it's 1 atmosphere. So that partial pressure of nitrogen is going to be equal to the same thing as its partial pressure. It's 0.78. The atmospheres cancel, so this is a unitless value because it's a fraction. It's a ratio. So with that information, if we know that there's 3.7 moles of air, we can use it to calculate the moles of nitrogen in that air using that mole ratio. So with that mole ratio equal to 0.78, the unknown here is the moles of nitrogen we have, and we can add in our given 3.7 moles of air total. Solving for the number of moles of nitrogen, we get 2.9 moles. And so this is a really nice way that within mixtures, we can use concentration to figure out the moles of a specific kind or the partial pressure of a specific kind of gas within the mixture. Now, other gas mixtures that you'll run into commonly, I guess commons depends on like the type of activities you're interested in. If you are going to be in a medical environment, you might see heliox. It's a combination of helium and oxygen that can be given to patients in the ICU. And it really helps for severe asthma or bronchitis. And we also see med gases. So if you go to the dentist and you have to have a cavity filled, sometimes they give you nitrous as a way to like dull the pain. It'll always be in a 50-50 ratio of nitrous oxide and oxygen. So that's a med gas too. Now, if you're a welder, there's lots of combination of gas mixtures that you're probably used to, but things like argon, carbon dioxide, and oxygen mixtures are going to be used in MIG welding, things like that. In the lab, we typically use argon and nitrogen mixtures because they're very stable gases that don't react with anything. So if something's going to react with the oxygen in the air, we'll conduct the reaction in either an argon environment, nitrogen environment, or a combination of the two gases.